Well, hello everyone. This is Todd Burke, and welcome to our lab, Dying Stars and the Birth of the Elements. So, we're studying chemistry right now, and this lab is based on astronomy, which is what we'll study at the end of the year. And the reason we're doing it now also is we're doing a little astronomy. We believe that all the chemicals that we're going to talk about in class, all the elements we've been studying, they're all created inside the core of stars, like our sun and bigger stars. We think that in the core of stars, the heat is so intense. Our sun, for example, is about 10 million degrees Fahrenheit. We think that's about the only place in the universe with enough pressure and heat to slam elements together at such high velocities that when they hit, they stick. That basically the atoms merge together and the nucleus ends up being bigger with more protons in it. And that's what makes bigger elements. So with the exception of hydrogen, helium, and a little bit of lithium, we think all the elements in the universe are made inside of stars. And some of them are only made when stars blow up inside supernova explosions, which occur when stars much more massive than our sun. And as they run out of fuel, they collapse. What happens is, we've talked about endothermic and exothermic reactions. Well, thermoneucleosynthesis, or fusion, the smashing together of these elements under incredible speeds, it combines them into making bigger elements. That process of fusion gives off a lot of heat. It's sort of a dream that someday we'll harness fusion on Earth and be able to have a really efficient source of energy, where we don't need a lot of fuel and we get a lot of energy out of it and would end our energy crisis. Okay, so let me say that again. First of all, here is our old friend, the periodic table, the elements. And what I'm saying is, you can see my cursor moving around, that not only is all the aluminum in the aluminum foil on your lunch today, or the silicon and the microprocessors of this computer, or the phosphorus and sulfur in the head tip of a match, or the chlorine they use to clean the pool at the aquatic center, the neon and the neon signs downtown. Not only are all those elements created inside stars, but that's the only place in the universe that those stars could have been made, those elements could have been made. So all of these elements originated inside stars and somehow left the stars, were spread out, recycled back into the universe, and then somehow came together on planet Earth so that we could make saran wrap and computers and match heads and clean water in the pool. Not only is that true, but all the carbon in almost every cell in your body, all the oxygen in every cell in your body, every cell in your body, nearly every atom in your body was forged inside the fiery furnace of the core of a star somewhere far away, somewhere in the past. What I'm saying is, literally, scientists think that you are made out of the stuff of stars that have blown up and spread out around the universe and then eventually come together here on Earth inside of you. Incredible that every one of us comes from stars. Even more incredible than that, I think, is this fact. You know, if I had asked my high school chemistry teacher, looking at the periodic table on the wall, if I'd said, hey, where does all that stuff come from? Back when I was a kid, most likely my chemistry teacher wouldn't have any idea. My chemistry teacher might make something up, might stammer around and pretend to know and say, that's the ingredients that makes up the Earth. And certainly if I'd asked, if my dad had asked his chemistry teacher, my mom had asked her high school science teacher, certainly then nobody on Earth knew this for sure. But now all scientists think, oh yeah, all this stuff comes from inside of stars, and it's something that's sort of washed over. We don't hear about it much. How incredible is that? You are made out of the seeds, the fragments, the bits and pieces, the guts of stars that have blown themselves up, spread out their innards throughout the universe, and then those are the building blocks for planets and animals and plants and life and you. That's what we're made out of. So, I like that story. That's a little background on why we're doing this. Where does the periodic table come from? Where are those elements made? Now you know. And the story gets a little weirder, a little more strange than that. So fusion inside of stars, excuse me, is an exothermic reaction. It gives off a lot of heat. That's why stars are so hot. Stars are constantly living in this perfect balance between the heat pushing out, the heat from their cores and the fusion they're in, pushing out, and gravity collapsing in these stars and trying to suck them in. And as elements are created, going through the periodic table, bigger and heavier elements, until finally we get to iron. All of a sudden, iron is a weird element. And when you fuse iron, it's an endothermic process. And that means it sucks in heat. And now you have gravity sucking in and the chemical reaction of fusion pulling in. All of a sudden, everything's pulling in, and that star collapses supersonically. That whole thing collapses and explodes, and we have the biggest explosions known in the universe. Light coming out of a supernova explosion. So the study of colors is called spectroscopy, and you're familiar with the colors of the rainbow. Spectroscopy is used to identify chemicals in a crime lab, or the ink from a pen, maybe in a ransom note. Well, when we're doing astronomy, we're looking at the color from stars and supernova explosions, galaxies and such. So what we know about light is that when white light is separated into different wavelengths, it runs through a prism, like this triangle represents, like a rainbow, we see them always in the same colors. Red, orange, yellow, that's Roy. G for green, blue, indigo, violet, Biv. Roy, G, Biv is the order of the colors of the rainbow. Red is the least amount of energy. Violet has the greatest amount of energy. Red is low energy, like radio waves. Violet is high energy, like ultraviolet, which gives you skin cancer. So we're going to look at all the light, all the electromagnetic energy from the supernova explosion. And then we'll be able to look at this fingerprint of which wavelengths are present and figure out which elements are present. So this might mean there's some hydrogen, some sodium, some calcium. Now we're going to do this looking at X-rays. So here's all the different kinds of light that comes out of a star. There's radio waves and infrared. Infrared is heat. Then we have this small section we can see with our eyeballs, Roy G. Biv. Then we have the ultraviolet, which is has a wavelength just a little too small for our eye to see. And it's more powerful, and that's why it gives us skin cancer. Even though these are all traveling at the same speed, the speed of light, we get down to X-rays and gamma rays, and they are much more powerful because they have tiny little wavelengths, which is what these squiggles represent. Really small, short wavelengths. Now, a supernova explosion is a huge, powerful thing. So we're going to be looking at high energy wavelengths, and we'll use an X-ray telescope for that. So this analysis of color and wavelengths of light is called spectroscopy, and that's sort of an introduction to our lab. Now, our data will come from this telescope. So I want to tell you about this X-ray telescope. This is the XMM Newton telescope. It's got these folding solar panels to power it, and once it was up in space, these unfolded and allowed it to be small inside the space shuttle and in space collect a lot of energy. It was launched into, well, let me say it's called the XMM because on board it has 3 X-ray telescopes, and it has 52 mirrors around each one, so it's called the X-ray multi-mirror telescope, and it's named after Sir Isaac Newton. Here's what the detector looks like in one of those X-ray telescopes. Here it is in 1999 in December, on top of the, or strapped inside of the space shuttle, ready to be launched into orbit. Here it is circling the Earth in its position in orbit. And here's a artist's rendition of it collecting data out in space. So let me tell you a little bit about supernova explosions. They are rare. In our Milky Way, we believe, lots of stars. We think not just thousands or millions, but billions. Not just billions, but we think 300 to 400 billion stars just in our little Milky Way. To give you an idea of how big we think space is, we think that there might be another galaxy in the visible part of the universe, there might be one galaxy for every star in our Milky Way. So we think there's, I don't know, 300-400 billion stars in the Milky Way, and that there might be another 200 to 300 billion galaxies that we can see in the visible universe. This one is a famous one, maybe the most famous, called the Crab Nebula in the constellation Taurus, and it is maybe the most studied. Some college professors have told me they thought you could teach everything there is to know about astronomy, every single different branch of study in astronomy, by analyzing the Crab Nebula. It's really beautiful. So here is our old friend, the periodic table of elements, and we believe the early universe had lots of hydrogen and helium and a little bit of lithium. And then all the rest of these elements are created inside the core, the bellies of stars. So we will talk more about this after discussing the lab when you're done with it. Here's another cool supernova explosion. This is the first one seen in almost 400 years, 383 years. This one was observed in the constellation Cygnus in 1987. It's kind of a neat situation where, first of all, our computer models predicted that supernova explosions happened in turbulent, crazy sort of ways, and this observation, a series of photographs and data, said our computer models were perfectly correct. That was exciting for astronomers back then, in the late 80s. This is Tycho's star, was observed about 400 years ago in Europe, in the constellation Cassiopeia. And then all of our data for our lab also comes from this constellation. This is Cass A. This is a supernova explosion shown here in radio waves. And here in radio waves again, colored a little bit differently. Here we have the radio, X-ray, and optical images all overlap to give us incredible details about the filaments. Isn't that just a beautiful picture? Well, I told you these were the biggest explosions in the universe. Let me just tell you how cool this explosion is. So this is where our data comes from in this lab, Cass A. And this is the largest radio source outside of our sun that we can find in the sky anywhere. So it's the greatest radio source, it's the greatest object in the sky that we can find that's emitting radio waves. And it happens to be outside of our galaxy, not just our solar system. And this happened about 400 years ago, around about 350 years ago, around the year 1680, and it was observed and recorded by a couple of people. Looking backwards, we think that must have been when it blew up. It's actually 11,000 light years away from us, and now, almost 350 years ago, we can calculate the temperature, and it's still 50 million degrees Fahrenheit. So this is a pretty amazing explosion. It's about 10 light years from side to side. It would take light 10 years to travel from one side of this explosion to the other side. It's huge, and it's still expanding incredibly fast. This thing blew up. Well, the image that we see is about 350 years from the time of the supernova explosion, and still what we see is the gas in the outer part of this supernova remnant is still moving away, expanding from the center of the explosion. It's still moving away at 10 million miles an hour. So this is a massive, massive explosion, the single biggest type of explosion or energy source in the universe. Now we have something like 3 to 400 billion stars in our galaxy, in the Milky Way galaxy. When we find one of these supernova remnants, supernova explosions, we can find about 2 a century per galaxy. When we find one, for a while that explosion is brighter than the entire galaxy. It gives off, in its brief death, it gives off more energy than the entire collection of stars in the average galaxy. It's brighter. Its explosion, is single burst of energy, is bigger than the collective energies of 3 to 400 billion stars all put together. These suckers are cool. Here it is in both radio waves and infrared. Here, this is the image taken by the Chandra X-ray telescope. And finally, we have the and make it a little bit larger. Cas A supernova explosion, this remnant of the explosion. Also analyze, so here we have spectroscopy showing the X-rays and the different peaks representing different elements. So this is how we then look at this picture in X-rays and analyze which wavelengths are present, and from that infer which elements existed in that star or were created in that explosion. All right, so here is our lab, and let me tell you now how to open the lab and log on. It will look like this, and the computer labs at school, you probably need to go to Programs, CLIA Exercises, and then find that icon. It's pink and it says XMM Lab for the XMM Newton telescope. And you'll open up a window like this. You need to go to File and Log On. Now, I'm going to have you log on as me so that you can change a few things. You want to type in instructor, INSTRUCTOR. Instructor. Oops, this should be all lower cases. We'll see if that matters. I've got my cap lock on. Okay. Have you finished logging in? Yes. And now we get a password. Now you want to put in capital C, capital L, capital E, capital A. CLIA, which is the name of our lab. Contemporary Laboratory Experience in Astronomy, CLIA. So that's our password. Good. So now what we have is some files. You want to make sure that this time zone difference says -6. It will not ruin your results if you don't get that right. And then click from the General tab over to Spectra. So in Software Options, there are these 3 tabs. Click Spectra on the right. And you want to make sure that this, which base photon count, which might read 80 for you, that's changed to 25. Base magnitude is at 14. And then come over to click on this red check mark, Fix Model Parameters. So what you want to make sure is, of all these many options here, you have the top corner and bottom corner on the left and the top corner and bottom corner on the right checked off. So that means the computer will already have the correct numbers for the amount of temperature, amount of magnesium, the absorption spectrum, and the calcium. So click OK. And then what we will be doing in the lab is trying to adjust some numbers for iron, silica, and sulfur to find out the right balance. So click OK and OK again. Save those parameters, yes. Do you want to retain access? No, you don't need that. Okay, so here we're now in the lab. Here's our picture of Cas A supernova remnant. We're going to go to File and Run Exercise. And here we have the XMM Newton Space Observatory, X-ray telescope. And we're going to go to point it at Cas A. Go to Hot List, Objects, and we already have the coordinates there. Just double click on them. That tells us the right ascension and declination. That's sort of like longitude and latitude. We'll click OK and yes. And now we can see that the right ascension and declination are moving. And there is Cas A now as viewed in X-rays. Well, what we want to do here in the crosshairs is point that telescope directly into field 1. So you're going to move by pressing the button east until you get the crosshairs inside there somehow, right, inside field 1. Now we're going to go to slew again. That's the astronomy geek term for move the telescope. We're going to slew to fields. That's not what I want. Chart field. There we go. So now we can see within that small. So look here. Here's the supernova remnant. Here is field 1. Within field 1, here are different targets. So we're going to go now slew, hot list, targets. Let's go to knot 4. And let's go to knot 1. And I'm going to double click on that. OK, yes. Now you can see the crosshairs moved and we are pointed directly at knot 1. As a class, we're going to analyze all 4 knots. What I want you and your 2 partners to do is just do one of the 4. You're going to be assigned one, and later you're going to share your data with everybody else. Okay, so That's what it looks like, zoomed in close on knot number 1. We don't want to look at it with our eyeballs. We want to use the X-ray telescope. So we're going to click on this instrument, spectrometer. Okay, so now that we have the spectrometer open, you collect data, you start collecting data by pressing go. Now this one won't work. I've messed up my home computer here by changing the program's parameters, and so I can't do anything. Right? But you'll press this button, you'll start seeing some fuzzy dots showing up in here, and you let it keep going. You want a signal noise ratio about 10. So you want to let it go for as long as possible. If you go up to 15, that's fantastic, and hopefully it'll only take you a few minutes while you sit and talk with your friends. When you're done, you have to click stop, and then what you have to do is hit File, Data, and save the spectrum. So you can name it whatever you want. Name it something, use your name maybe, and the date, and then save it. Okay? So now what you can do is you can actually close the spectrometer. Coming back to our main screen and click on Tools, Spectrum Analysis, we now have a window opened with nothing in it. So we're going to say Screen Display, Show Difference, that's good. File, Load Spectrum. So we're going to load a spectrum that you took. I used one I'd done a couple days ago. And I'm now also going to do load a comparison spectrum. So now this is, down here what I have is data we observed and light we collected in the X-ray part of the spectrum by pointing our telescope at Cas A supernova remnant. That's right here. This is our data. But we're going to now compare it to File, Tools, Comparison Spectrum, compare it to a known model. So here what we have is what we would expect it to look like if we were to just predict how things look in the laboratory. So this is the spectroscopy of various elements. And we can change things around here by playing with these slider bars. So over here we have temperature is fixed, magnesium is fixed, we can't change those. Absorption and calcium are fixed, but iron is not fixed. We can mess with that. We can change by pulling on these slider bars and dragging them around. We can change the amount of silicon, and the same thing with sulfur. And our goal is to get this model to look as closely as possible to what we found with our data. So we want to kind of right away make some adjustments just based on how things look. That doesn't look good. I like those little lines there. I want to get rid of that thing. So we're going to make this look as close as we can, something like that. Okay, so that our model of known elements matches our model of our data from Cas A, and then what ultimately we have is some numbers that tell us the amounts of iron, silicon, sulfur, which is what we need for our lab. Now, another thing you do as you get close is look at the red line here. The red line is the computer comparing these two, and when this line is flat, it means there's no difference. They're exactly the same. So as I adjust something here, you can see that now I've got way too much in this part of the spectrum, and I've got a much bigger difference here. And as I remove that difference, as this mountain becomes a valley and flattens out and becomes more like this one, the red line will end up becoming smaller until now this little peak is about identical to this little peak, and so there's no difference in the red line in this part of the spectrum, at this wavelength. The red line is right along the 0 point there. So that's good. You see how we have a difference out here? So we have a little difference on the red line. This our data is a little bigger than the model. So we have some differences here, but this is pretty close. You want to get as close as you possibly can. And then what you're going to do is compare it. So this worksheet is going to ask you to write down your data here. So let's say that your group wrote down the data for knot 1. Okay? And there might be some other groups doing the same thing. There could be 1, 2, 3, 4, 12 groups in the class. Groups of 2 or 3 students. You'll put in your data here and get the data from everyone else in the class. Then you can average together all the people who got data for knot 1, and then what number did they get for iron? what number do they get for silica, what number do they get for sulfur, and put the average down here for each one, iron, silica, and sulfur. And then you want to get the averages for knot 2 and averages for knot 3, and then you want to average those together and give the most averaged rounded figures, maybe remove as much error as possible. So we'll focus on iron for that part here, the iron average. Now let's see here. If we continue down, you'll find you have some questions. So you want to answer questions 2, 3, 4, 5. If you're an honor student, you want to read those questions, answer them, but know that you'll be graded. This stuff will be on the test, but we'll talk about it as a class. But what you have is this assignment. You want to do some math and answer questions 6, 7, 8, 9, and 10. Okay? Anybody can answer the 2 bonus questions, and if you were to do that, that would be extra credit. So there is your lab, Dying Stars and the Birth of the Elements. If you have any questions, help each other out. All the information you need is in these video directions. And if you forget something, you can just rewind or click back to that part of the video and then see if it helps you to hear it again. Enjoy, and we'll finish off some chemistry in the next few weeks and finish off the year with some more astronomy in May.